Hello everyone. This is the first lecture of the course Statistical Thermodynamics. The topic for this lecture is understanding what statistical thermodynamics means. So, the question we are going to address is, what is statistical thermodynamics? Let me begin answering this question by considering the place of statistical thermodynamics in physical chemistry. Of course, the scope of the subject is wider than just physical chemistry, but our focus will be more on physical chemistry aspects given the context of this course. Physical chemistry, as you know, is concerned with applying the laws of physics to chemical systems, namely to atoms and molecules, to understand the structure and properties of matter and the transformations of matter. The area of physical chemistry that helps us understand what drives the transformation of matter is thermodynamics. Now, thermodynamics has two different approaches of study and application. The first approach considers the so-called macroscopic or measurable bulk properties of matter like its temperature, pressure, energy, and entropy, and describes relationships between these properties. This area is called classical thermodynamics, and you have all encountered it in your earlier years. The second approach, sometimes called the microscopic approach, begins by considering matter to be made up of particles, essentially atoms and molecules, whose properties can be understood using quantum or classical mechanics. It turns out that the study of the distributions of the properties of these particles can help connect the microscopic properties to the macroscopic or bulk properties of matter. This is the subject of statistical thermodynamics. So, statistical thermodynamics is a bridge between the microscopic world of atoms and molecules, whose properties are described by quantum or classical mechanics, and the macroscopic world of matter that we interact with and whose properties we observe on a regular basis. Statistical thermodynamics is also sometimes referred to as molecular thermodynamics or statistical mechanics, and I will use these terms interchangeably in my discussions. There are a few comments I would like to make about each of these two approaches. Speaking of classical thermodynamics, an important point to note is that measurable macroscopic properties are not always well defined. They are only well defined when the system is in thermodynamic equilibrium. This is not the case for microscopic properties. I will return to the concept of equilibrium when we discuss classical thermodynamics in detail. A related point is that thermodynamics does not tell us about the dynamics of the system. It can only tell us if one equilibrium state is more favorable than another equilibrium state. But it's silent on what happens to the state of the system when it is going from one equilibrium state to another. Now we come to statistical thermodynamics. You know that atoms and molecules are described by the laws of quantum mechanics, and in some cases to a good approximation by classical mechanics. A bulk system is made up of a large number of molecules of the order of 10 to the 23 molecules. Obviously, if the properties of every particle in a system is known, that is, the microscopic properties of the system are known, it follows that the macroscopic properties of the system are known as well. Microscopic properties can be obtained at all times, not just at equilibrium, unlike measurable macroscopic properties. But the problem is that keeping track of the properties of each and every atom or molecule is practically impossible. In other words, applying quantum mechanics to this entire system is not practically possible. Interestingly, it turns out that we don't really need to know the details of each and every particle to know the bulk properties of matter. Molecules are moving and bumping into each other and exchanging energy, and the energy is distributed among them following rules of probability, and this distribution of energy, not the precise energy of each particle, determines the bulk properties of matter. It turns out that these distributions have specific forms, and bulk properties can be extracted by a statistical analysis of these distributions. This is the basic idea of statistical thermodynamics. Besides connecting microscopic properties to macroscopic ones, statistical thermodynamics gives more information about the behavior of matter than classical thermodynamics. It can connect molecular structure or the chemical composition of a material to its measurable thermodynamic properties. It can explain physical changes like phase transitions based on molecular structure. It can explain why some reactions take place while others don't. Moreover, statistical thermodynamics gives new layers of insight into properties of matter which were not accessible with classical thermodynamics. For example, it gives a physical picture of heat that makes the first law of thermodynamics obvious. Importantly, it demystifies the concept of entropy and gives us a beautiful physical and intuitive feel of this otherwise enigmatic property. So, statistical thermodynamics can allow you to look at nature in a way you could not have done otherwise, and I think this is really exciting. In the next lecture, we will look at a brief history of the development of statistical thermodynamics. See you for that.